Okay, we got now. Okay, Apple Pencil have no battery, so we'll see how much we can do.
Okay.
Can you see? Can you see?
Yes, yes, yes. We can see your slide. I mean iPad.
Okay. So right. So right. The question is quantum well. Quantum well, quantum dot. So what is it? Okay, the semiconductor that we are talking nowadays, you know, the one we did in the class. Generally, we call it bulk semiconductor. Bulk means is big. Bulk means it's big. Okay, so anything bigger than, I think, 100 micrometer, 100 micron is called bulk. Okay, then you have, if you slice, I slice this if I slice this semiconductor, I make it thinner, I can make it I don't know whether I can draw this or not.
Bigger than 100 micrometer, you say?
Yes, 100 micrometer, or I think 100 micrometer, or if not 1000 micrometer. It is big. So if I slice this semiconductor like this, right, to be like this. I don't know, you can see 3D or no, but if I take a slice of it, right, and then the slice is, and you can see in a bulk, even a bulk semiconductor, the electron travels all direction, right? Any direction it can travel. But if I take the semiconductor to this, to a smaller proportion, okay, let's say this quantum well, the roughly, I can't remember, if you Google, I think roughly it could be hundreds of nanometer, right? Is it right? Apa nama, Anas? Did you check? Hundreds or
Not sure.
thousand or hundreds of nanometer. Okay, bulk is like bigger than, like, I'm sure more than 1000 micrometer is called bulk. Quantum well, if you make it smaller, you cut it and make it smaller, if 1100 nanometer in terms of dimension, and what happens is the what do you call it, the semiconductor, the free carrier only can move in two direction. So the electron can move in this direction and also in this direction. It's like two direction. It can travel through that and then to here.
Is the nanometer in terms of length or volume?
Good question. In terms of here, this the cross section.
The area, the cross section area.
Yeah, this area.
I think it's the length.
This is the length. So it needs to be the cross section, because you know when we talk about volume, we say current, the current density equals to the current divided by the area, and here's the area, the cross sectional area. This is the length. This is the area. So if you make, so the current will flow like this. Okay, so this called the current. I is current density.
Okay.
So if you make it smaller, okay, so basically you're slicing semiconductor to make it smaller. If it's small enough in the range of what you call it, 1,000 or 100 nanomicron, it becomes quantum well. What does quantum well does? It only allow carriers to move into two if I'm not mistaken, two-dimensional. Okay, because what happens if it's confined? They got the word is confined. So the carriers are confined. Confined means it cannot move freely. It can only move into a certain direction. And if it's confined, it means that the probability for it to recombine is faster because it's confined to a smaller space. Quantum dot. So you have bulk, quantum well, and then you have quantum dot. Quantum dot is basically the same semiconductor but you cut smaller. So for example, it comes a very small area. So normally it's 10 nanometer by 10 nanometer by 10 nanometer, something like that, or smaller. Okay. So what happens is when the semiconductor is very small, the electron cannot move. It will just stay there. It has no space to move. It cannot move. So basically, then okay. So if you have if I draw a heterojunction, it is a heterojunction. It can be an LED, it can be a laser. So you have a higher bandgap material over here, maybe indium gallium arsenide, and then you have a
Adam,
yes.
Alam asks to join the class in the WhatsApp group.
Thank you. Okay, it's joining. Right. Where was I? So this is what do you call it, the heterojunction. So it can be LED, it can be laser, it can be any diode, it can be even solar cell. Okay. So what happens is, so you have a big semiconductor sandwiched by a smaller semiconductor band gap. For example, gallium arsenide here. This, this length, if it's a bulk junction, this length will be like in like 100 micrometer or 1,000 micrometer, this length. Bulk, I mean big. But if you want to change it, you want to put quantum dot in there, I can put indium arsenide quantum dot. And indium arsenide is lattice match to gallium arsenide. So I can rub this off. So I can put it rubs the whole thing. That's why I rub this thing. Cannot. It will rub off the whole thing. So let's say I'm drawing I want to make a quantum well. You see? So the blue is the quantum well. I make the dimension smaller, and then this material here, is the indium arsenide. So I can use another material to make it a quantum well, or I can make a gallium arsenide quantum well. So I just make it smaller. So I have indium gallium arsenide with a gallium arsenide quantum well. I just play with the dimension here. Okay, so I can make gallium arsenide as the quantum well, or I can make indium arsenide as the quantum well. Quantum well just means that you reduce the dimension, make them smaller here. Okay, if I want to make
for the first picture, the picture above, is the blue and the red drawing the same LED?
The blue and the red drawing the same LED.
Part of the same LED,
no,
or is it just to show the size?
Understand. So it just means that it's a different. is a, so the red one is a heterojunction bulk heterojunction LED. The blue, meaning the blue,
Yes.
this blue is a quantum well LED, quantum well heterojunction LED. When you say quantum well, it will be automatically heterojunction. Am I answering your question?
Yes. Yes.
Okay, so I can make a quantum well out of three material here. The apa ni, the indium gallium arsenide, then the gallium arsenide sandwiched by indium arsenide. So indium arsenide is the quantum well. Or I can make like this at the bottom here. Indium, the quantum well is the gallium arsenide. I just make the condition is that it must be sandwiched. It must be heterojunction. It must be sandwiched by a larger band gap material, right? And you need to be smaller than the 100 nanometer. If I'm going to make this a quantum dot, just simple, just make it smaller. Okay, so so this is will be around 10 nanometer. So this can be gallium arsenide, and this can be indium gallium arsenide. So what happens if I make it smaller? So when what you call it, when carriers travel, it will be trapped inside the quantum dot. This electron travel, it will trap inside the quantum well. Okay, heterojunction, it will trap inside the bulk. But you can see this is quantum dot is the best because it will trap and the electron will not move and will recombine here. The other thing that the speciality of quantum well and quantum dot is that if I first is trapping, the other one ialah is this. I'm exaggerating a quantum well. If you read the literature, you will see you will have discrete energy level. They call it discrete energy level. What does it mean? It means that, so this is quantum well, this is small enough where previously, like if it's a bulk like this, if it's a bulk, the the energy level is continuous, right? Remember I told you, if it's a bulk semiconductor, the energy level is continuous. There's no gap, right? Yes or no? Yes, right? So semiconductor, the energy level here is continuous. So heterojunction bulk, anything bulk is continuous. But when you make it small, the energy level becomes discrete. Okay, discrete. What does discrete means? There's a gap, okay, between one energy level and the other energy level. So what is the advantage of this? The advantage of this is that when you have recombination, you can have a clear, nice wavelength. Because if, for example, if this, if the energy between the conduction band of this level to this conduction band of this level, say 1.4 eV, you will get a sharp 1.4 eV. Very nice. But if a heterojunction, you will okay, wait a second. If a heterojunction like this, you will recombine here, but you can also have a slightly small, slightly bigger. You understand? The wavelength is not nicely 1.4. There'll be slight difference. There's like a variation in terms of the recombination energy. However, if quantum well, you will see discrete. Okay, what happens if quantum dot? Quantum dot is the same. You will still have this discrete energy level, except for it becomes larger. The separation is larger. For example, if I going to exaggerate to draw about the quantum dot, so it will be less. It will be here. It will be here. You know. So there's, you can have recombination here, you can have a recombination there. So you can see the separation from here to here. the separation of the energy level here is bigger for quantum dot. That's the difference. So which means that you have a cleaner recombination, more clearer, defined wavelength. Okay, so quantum well also, but quantum dot is very expensive. As you go as quantum well to quantum dot, it becomes more expensive. So quantum dot is very difficult to make and very difficult to control. Okay, this quantum dot. I did my PhD in quantum dot laser. I didn't make the laser. Somebody else grew the laser. I characterized. But to make a coherent or something that reproducible quantum dot at that time is difficult and expensive. Millions of dollars of equipment. However, quantum well, it's slightly cheaper. Previously, it was expensive. Now technology become better. Quantum well is cheaper. So now, if you look at a lot of LEDs using quantum well, but if you want a good performance laser, you do quantum dot. But you need to trade in between performance and cost. Normally, like people don't go for quantum dot because it's expensive to make. So they are happy with the quantum well. Okay, and another thing, the advantage of quantum dot and quantum well, quantum dot especially, is it's less sensitive to temperature. Is less sensitive to temperature. As we know, starting of the class, we talk about the effect of temperature to semiconductor. It's very, very sensitive to temperature, right? So if it's sensitive to temperature, it means that it can increase the dark current. It can, so you suddenly have a lot of current where you don't want current. And also it's not good for, in terms of maintaining the junction temperature. It means the operation of the device. So, but quantum dot is good. One of the, if you read one of the advantages, it's less sensitive to temperature because of this. You can see here, because of the large energy difference in terms of the discrete energy level. But for heterojunction, it's very close packed together, so it's sensitive. You can move here, there very easily. Okay. And so you can go, so basically that's the basics of quantum dot and quantum well. If you want to know more, there'll be another class. Okay, any question?
No.
Mm-hmm.
How would the traps or defects in quantum well or quantum dot be like?
It's the same, because when we talk about trap and defects, where's the trap and defect? Where does it, if you're going to draw inside the energy band diagram, where would it be?
The heterojunction.
It can be here. It can be here. It can be anywhere inside the band gap. So because here, this area, if I go into this area here, is all band gap, right? The green area. So the trap can be anywhere inside the band gap. So it can be anywhere. It's still the same concept. So you can, if the recombination is here, for example, if the recombination happens in the quantum dot or quantum well, so the trap over here will not make much difference to the recombination. It doesn't matter, right? But here it matters, because you can have it goes here and then go there, and then you have like phonon coming out because it's not direct. Okay. Any other question? No? Good, you understand? So you can answer question on quantum dot and quantum well later. Good. So you can read, you can Google what's the advantages of these structures. So that's why we engineer, they make this fancy structure not for fun when we do research, because we want to improve the performance of the device or of the material. So we make structures like quantum dot, quantum well, because first, you know, interesting. Most of it they discover it theoretically first. They do the physics, do the mathematics and everything. They say, oh, by if we confine the carriers in 3D, we can get better, recombination and better, temperature sensitive. So the physicists will do all the mathematics and then they prove theoretically. Then after that, they pass to the scientist or researcher to make to realize it in real life, right? And then they will see there's a lot of problem. So until now, quantum dot, I don't think it's very easy to make. In the semiconductor quantum dot, I'm not talking about if you go for OLED, they have OLED, they have this chemical quantum dot, what do you call it? Quantum dot chemical, something like that. It's very easy to make. That's one easy. You shake, it becomes very small, tiny dots. Then it's called quantum dot as well because it's luminescence, but it's not semiconductor. To make quantum dot is quite tricky and use a lot of money. And you need to be very skillful. Okay. Any question? No, we have like 8 minutes left. So after this, Alam, can you present? Okay, so after we're going to have a break, like 3 minutes break, and then after that, Alam will present on photo detector. Then we complete the optoelectronic devices. Next class, we can go to BJT. Because this, MCO, PKP, I'm lost of the week. I don't know how much. We'll try to cover as much as possible the syllabus. We cannot, then it's okay. The exam will be accordingly. Okay. But you really want to learn the extra syllabus which we not covered, I can teach you one by one after that. Okay, now because during this time, I think they will forgive us if we don't manage to cover a lot of material. Semua lost. Saya lost. Kan? Iman lost lah. Right. Okay, so any question more on so you don't have question on laser?
Yes, ma'am.
You have 7 minutes.
Ma'am, is the are the recombinations more prominent on P side? When we have recombinations, on which side are the recombinations more prominent?
More prominent?
Yes, ma'am.
If it's a PN junction with no I region, you mean?
Yes, ma'am.
It's the same.
It will be same.
Yeah. Why should it be different?
Ma'am, I read somewhere that it is prominent on P side because there will be a lot of this electrons, minority carriers on P side because electron mobility is higher than the hole mobility. So there will be many these large number of electrons on the P side and minority carriers. So it was written that there will be more recombinations on the P side.
Recombination is when free electron meets free hole, or free hole meets free electron, right? So they're saying at the P, but aren't we forward biasing the junction? So forward bias, we are not talking about minority. We're talking about.
Can I send you that note?
Yeah, sure. You can send it to me. I will read it and then we discuss in the next session. Okay, good. Anything else? No? Everybody understand?
Just some question from quantum well. So the quantum well should have discrete level of energy.
Yes.
Means that there is totally no carriers between the discrete level, is it?
Yes.
They will just jump to another level.
Yes.
About the quantum, the discrete levels, what determines the gap between the levels? Is it the material or the dimension?
Good question. There are a lot of factors that determine the level, the difference in the level. The material also plays a role. There are a lot of complicated mathematics which I'm not covering. But generally, it's the material will influence the what they call it, the difference energy level, the discrete energy levels in the quantum well, and the size. That's the beauty of playing structurally, playing with the material. You make it quantum dot or quantum well, you make it slightly bigger, the gap will change, or slightly smaller, it will change. So that's why we say we can actually determine what wavelength we want it to come out by playing with the size of the semiconductor. If you Google, there's a university, I can't remember who have like a not a software, like a website where you can put dimension, you can see it will do the mathematics at the back, and it will show you that it's changing the discrete energy level, and you can change the material there as well. Ada university in US, I think, who made that. If you Google quantum well, not sure, quantum well simulation ke, I think simulation on the discrete energy level, maybe you will find it. Okay, other question? No? Right.
Yes, ma'am. I studied the energy bar diagram, but I'm not. Uh, I'm not. It is not very clear. Can you just explain for 1-2 minutes only,
Energy,
roughly?
which one?
Yes, ma'am.
I
For
don't,
laser and LEDs.
oh, you mean the how it works?
Yes, ma'am.
2 minutes, huh?
Yes.
We only have 2 minutes. We'll come back. I'm afraid it might take more than 2 minutes. So after 2 minutes, I will explain how the laser and LED work. Okay?
Okay. Okay, ma'am.
All right.
And the recombinations depend on a number of minority carriers. When we will forward bias it, then the carriers will go to the opposite sides and they will recombine there with the minority carriers. When we have forward biased a PN junction,
Huh?
when they enter the new region, they will then get involved in recombinations.
I don't.
I mean, when holes will go from P to N side and electrons will go from N to P side when we have forward bias junction.
Anybody understand Tamana's question?
It's breaking up.
I don't understand. It's okay. We have less than a minute. Why don't you write properly think properly the question? Ask me after this, okay? We'll have a 2 minutes break. Okay, Assalamualaikum. I will record now. To answer your question, Tamana, I read your article. It makes sense. So basically, because the rate, it talks about the rate of recombination.
Yes,
When talk about rate of recombination in the P, logically it be faster because
yes,
when you pump carriers, right, from electron will come from N to P, hole will go
yes,
from P to N. However,
yes, ma'am.
electron is faster because
Yes,
it's lighter, so it will arrive to the P faster than hole arriving to the N, right?
yes, ma'am.
So because of that, the recombination rate will be slightly more at the P. Yes, that's right.
On P side.
Yes.
Oh, is it then on the P side there will be more recombinations?
The recombination rate there will be higher.
Higher. So will it be more luminous on the P side?
Cannot hear you.
Ma'am, will it be more luminous on the P side because recombinations lead to the emission of photons?
Yes.
So if there is higher rate of recombination on P side, there should be more photons also
Yes.
on.
Yes.
Okay.
Yes.
Madam, I also have some question.
Okay.
Inside the LED, the emission, what we call emission surface, emission plate. It is said to be as thin as possible. What happen if the emission plate, the one at the surface, is much thicker?
Okay. Do you understand what is emission plate?
The between the junction layer, there is where the highest probability of photon emitted.
No, you're talking about the. Can you repeat your question again?
Actually, what is the difference between thinner and thicker of emission plate? I think the one surface inside the LED.
So then my question was, what do you understand about emission plate?
It is where the most of the recombination happen, and the emission, the highest probability of emission of photon.
Okay, I will tell you.
No?
When okay, in a semiconductor, there are a few things that will happen simultaneously. Yeah, it can happen at one time. What is recombination? It will so if you free electron meets free hole, it will recombine, right? But also in a semiconductor, what will happen is absorption can happen, and this principle of absorption, which is important in what do you call it, in the photodetector, right? So absorption can lead to what do you call it, the as what do you call it, you exciting the free carriers to the conduction band. Okay, so when and for LED, right, you don't want absorption or what you call it, generation to occur. Sometimes we use the name generation. Okay, you don't want generation to occur, you want only recombination, right? But in life, both will happen. You will have both happening at the same time. You have recombination and you have absorption. So you want to promote a lot of recombination, and you want to reduce as much as possible the absorption or the generation. That's why if you make the area thin, because the absorption will depend on the thickness of the material of the semiconductor. If you have more semiconductor, it will absorb more, right? So if you make before it goes out, the light, okay, the frequency will recombine inside the semiconductor, and the light need to comes out, right, for you to see. For us to see, the lights need to come out of the semiconductor device. So before it goes out, so you want all the lights to go out. You don't want any of the lights being absorbed back, right? Because the light because light is energy. The energy can be used for generation. You don't want any generation. You just want the lights to come out so that you can see, your eyes can see. So if in order to do that, you need to reduce the thickness of the near the surface, because when you have recombination, it wants to go out. You don't want to make it thick. You make it thick, it will go here, it will absorb before it goes out, right? So that's why we want the surface, whenever you have recombination, the thickness is like very little, so that light comes out from the semiconductor. Okay, boleh. Alright. I don't know where's Alam supposed to present. So I will now discuss about the question on the, what do you call it, the laser LED. Yeah, boleh?
Yes, ma'am.
Okay, I'll share my iPad now. Can you see?
Yes, ma'am.
Good. So now the I'm doing the P, and then if it's a forward bias, the Fermi level of the N should be slightly higher.
Ma'am, is this Fermi level near the conduction band?
You are right. Correct. Strong. That's why I was saying, why my draw is. You're right. Level of the P at the valence band, and then the N should be slightly up. So this is normally how I draw it. And then sometimes you need to read the question carefully. Sometimes I give the carrier concentration, no, the doping concentration. So it needs to be reflected inside the drawing. So if the P is more highly doped, right? If the P is more highly doped, this Fermi level here, I will rub it off. It should be, you need to show it like actually closer to the, can you see the difference, relatively difference? The P is closer, the Fermi level is closer. So it shows that the concentration, the doping concentration of P is higher compared to the N. Okay,
Yes, ma'am.
so roughly if I make this a junction, okay, so this is a LED, and then how does it work? Basically, it's just you forward bias the P and you reverse bias the N, and you have a lot of electron will diffuse to the P and hole will diffuse to the N, right? So this, when I talk about this, is a normal LED homojunction. Maybe if I want some fun, I'll put the exam question heterojunction. So you need to read the question carefully. The P made of what? Or I say Pn the same material, I is another material. So you need to draw accordingly. Yeah? So electron will diffuse from N to P, hole will diffuse. So the word is diffusion. Make sure you use the right word. Okay. And then when it diffuse, so the free carriers will meet each other. So electron will recombine with the hole here. So you have recombination. And when you have recombination, you will release energy of the same energy of the band gap. So you have one photon coming out with the energy of the band gap, the same energy here. Right. So if the depletion region here a different material, it will follow the the recombination of the I region. If it's quantum well, it will follow the recombination of the quantum well. But let's say in the question, I only give you the band gap of the quantum well material. So for example, the quantum well material is gallium arsenide 1.4 eV. But you know that quantum well has discrete energy level, right? Which means that if like this, 1.4 eV is this. But you know, in quantum world, there will be discrete energy level will be slightly higher than the bottom one. So this recombination is the light photon, is it bigger or less than 1.4 eV?
Bigger.
It should be bigger, right? So the light that's come, if it's a quantum well, if I use a 1.4 of a gallium arsenide, the light that comes out may be slightly bigger. But if you can say, out of assumption, we can say 1.4 eV, I will still give you right. But if you say it's 1 point maybe greater than 1.4 eV, 1.5 eV, I will still accept. And maybe you get more marks for considering that it's actually discrete. Okay. So basically that's all. So you have recombination, you have photons come out, and you need to say what is the energy of the photon that comes out. That's all. So the so this is LED. Laser is the same. You have recombination. The only difference is you need to have a when it recombines, it recombines over here, it needs to go through a you need to recombine and then mm, and
It
you need to,
needs stimulus.
sorry.
In laser, we have to give stimulus.
Yes, before if you have even you have a stimulus, right, of this
Mhm.
energy, but you need to first fulfill the population inversion first criteria. If there's no population inversion, even if you put a stimulus, nothing will happen, right? So you need to have the Fermi level of a laser should be higher up here. So the Fermi level of in population inversion, the Fermi level is inside the conduction band for electron and inside the valence band for hole. So when you achieve like this, you know you already entering population inversion because there's more free carriers here. Then if you give a stimulus, then the recombination will be helped by the stimulus, and you have the monochromatic the same phase and all the criteria of a laser light. So you need to make sure it's in population inversion first. How to make a population inversion? Number one, you need to pump a lot of electron in. How to pump? You increase the voltage. You increase the voltage, you have a lot of free carriers moving. And number two is the mirroring. Okay, so we talk about mirroring. Warna hijau sini, mirror. We have a mirror here. So basically, the light will hit there, hit here. It will keep on bouncing. So when it becomes like LED first, it will recombine, but then it will move inside the semiconductor and it will hit. It will be reflecting, comes out, and it will help in the population inversion. Okay, right? So when you have lots of light traps, you will improve the population inversion because you are promoting electron to go here. The light energy that being produced are being pumped there. So in the end, until you get full population inversion, and once stimulus come, then the rest of it, all the light that comes out will follow one characteristic, which is the same wavelength, the same phase, the same direction. Okay.
Ma'am, does that mean can we use these degenerate semiconductors because they will also have Fermi levels inside?
Uh, Again, can you ask the question again?
Um, you said that we need to have Fermi levels in the p side inside the valence band
Uh-huh.
and on the n side inside the conduction band.
Uh-huh.
Does that mean we can use these degenerate semiconductors?
Yes, degenerate means that the Fermi level is in the p or for in the p for n for electron and for n side. So, no, let me correct. Degenerate means the Fermi level is inside the valence band or conduction band. Okay.
Yes, ma'am. So, how is that achieved? Is that achieved by doping excessively?
Yes. However, degenerated semiconductor will help make the population invasion faster because you already have a lot of that. You need some. You need to still pump current. You need to still flow. So, what was your question?
That means we can or cannot have a degenerate semiconductor, but if we have a degenerate semiconductor, it will help.
Mm,
This. Okay.
yes.
Okay, ma'am. we don't necessarily have to use a degenerate semiconductor. Is that true, ma'am?
I
We
cannot
don't
hear
have
you.
to use. Huh?
You don't have to. Because
We don't.
degenerated semiconductor have a lot of problems. Go and Google why they don't use degenerated semiconductor. There are other problems. There are other limitations. So you can go and
Okay,
find
ma'am.
out what are the limitation of degenerated semiconductor.
So we have to shift these Fermi levels inside the conduction and valence band by pumping.
Yes, that's the best way because that will
Okay, ma'am.
be will give you the less defect actually.
Okay, ma'am.
Okay. Anything else?
No, ma'am.
Okay. Where's Alam? Can somebody type there in the WhatsApp asking?
Uh, he's asking you to let him join.
Oh
He
really?
says,
Okay. Okay, Alam, are you there?
Yes, bro.
Why did you join late?
I just was thinking that no message, but my phone was silent. I didn't hear the tone.
You watch lah. I say only 2 minutes break. Okay. Now Alam, your turn to present.
Okay, bro.
I have a loud sharing. So the rest of you, you only have like 15 minutes, huh? Alam.
Okay, bro. So can I proceed?
Okay, please proceed.
Respected professor and brothers and sisters, Assalamu alaikum wa rahmatullah. Today I will present on photo detector. So let's go to the outline. So here I will cover classifications of optoelectronics. Basically, photo detector is under optoelectronics. And then we will also talk about the history of photo detectors or opto detectors. Then we will learn that what is photo detector actually called. Then we will discuss about photo detection principle and modes of operation of optical detectors, laws of conservation and optical absorption, types of photo detectors based on PN junction, and then inshallah Islamization and references.
Okay, skip the history, yeah? You can skip the history.
Okay. So photo detector basically is under optoelectronic device, and photoelectromotive. Photo detector is under optoelectronic device, and photo detector basically classified in two types. But we will look to the electromotive element on based on PN junction. So based on PN junction, there are three types: photodiode, PIN diode, and LPD. So here's the history. Later on, we can. So what is photo detector? Basically, semiconductor devices which can be implicated to detect the photons present. Such devices are known as photodetectors. Means, that can detect the photons or lights and can convert into electrical energy. So that is called photodetector. Means that they transform optical signals into electrical signals when excess electrons and holes are generated in a semiconductor. So means photodetector is a device that can sense photons or light and can generate in electrical signals. So there are two principles of photo detection. One is external photoelectric effect, and another one is internal photoelectric effect. So basically, in external photoelectric effect, electrons become free from the metal surface by energy absorption obtained by streams of incident photons. But in internal photoelectric effect, free charge carriers are generated by absorption of incident photons in semiconductor junctions detectors. So here we can also distinguish between external and internal photoelectric effect. But one thing is important here that responsivity, spectral response, and rise time is matters in photo detection technique. So here is the mode of operation. We have two types of operation: photoconductive and photovoltaic. So in photoconductive, we have the photoconductive mode here and photovoltaic mode here. So the photodetectors are operating in photoconductive mode and also photovoltaic mode. So if we go to the next slide, we can see photoconductive mode. So basically photoconductive mode, there is a mode where the diode is operated in reverse bias, which in turn dramatically reduce the response time at the expense of increased noise. Consequently, faster response times can be achieved by increasing the depletion layer and decreasing the junctional capacitance. And the photocurrent is linearly proportional to the luminance for the given spectral distribution. So this happens in photoconductive mode. But in photovoltaic mode, this mode exploits the photovoltaic effect, which is the fundamental for solar cells. But normally our photodiode, that one we use photoconductive mode, this mode. So when used in zero bias or photovoltaic mode, the flow of photocurrent of the device is restricted and voltage builds up. So this is mostly suitable for the solar cells. Solar cells also kind of a photodiode, but as we are talking about the photodiode, so normally photodiode they uses photoconductive mode. If we talk about the characteristic curve for the operating modes, so here is the current versus the light intensity. So we can see that in photodiode mode, when the light intensity is increases, the current also increases. The light intensity increases, the current also increases in reverse bias. As photodiode mode, photoconductive mode, it works in reverse bias or photodiode mode. If we talk about current voltage characteristic, also we can see that normally we will learn in the working principle that how photodiode works in reverse biased mode. So we can see reverse bias mode. But when it works in reverse bias, even though there is no photon or no light, there is a minor current that is called dark current. So we can see here this is the dark current. It is very less due to reverse bias condition. But when the light intensity increases, then the current also increases. From this curve, we can see when the light intensity increases, the current also increases from here. So to achieve more current, we need to have more light intensity to create more electron and yes, to create more electron holes. So basically in here in this technique, optical absorption occurs. Optical absorption we also learn in laser. The principle almost similar. So here interaction in semiconductors as far as devices are concerned in band-to-band transition, and also in the photon absorption process, a photon scatters an electron in the valence band, causing the electron to go into the conduction band. And these two processes are of obvious importance for light detection. So absorption, like when the electron is at the ground state, then the photon or the light absorbed by the electron and the electron become excited. So it goes to the higher energy state. So this basically called the absorption. And also we have electron hole photo generation. So most modern photo detectors operate on the bias of the internal photoelectric effect. Basically, the photo-excited electrons and holes remain within the material, increasing the electrical conductivity of the material in a semiconductor. So electron hole photo generation in semiconductor basically absorb photons, generate free electron hole pairs. And then the transport of the free electrons and holes upon an electric field results in a drift current. So basically, the photoelectron, we just receive the drift current from here. I think I should explain the working principle, then we will know about the drift current. Before that, I just want to say that there are three types of photodetector: photodiode, pin photodiode, and avalanche photodiode. And we already have learned that what is photodiode. Basically, that senses the light and convert the photons into electrical signal. So this is the photodiode equivalent circuit, and the performance also matters in the capacitor and the resistor. There is called parasitic components RD and CD. That also plays an imperative role on the performance of the photodiode. So this is a photodiode working principle. So basically, uh, from here we can see the photodiode symbol. This is a normal. This is a normal kind of normal diode, but it has two arrows here. Means it absorbs light or it senses light. But it also has like normal diode anode and cathode. So photodiode working when working of the photodiode is based on internal photoelectric effect. Free charge carriers are generated by absorption of incident photons in semiconductor junctions detectors. So that normally the diode is connected in reverse bias. The photodiode works only in reverse bias condition. So when it works in reverse bias condition, I think when it works in reverse bias condition, so normally a minor current that is called dark current or drift current, that one flows from P to N junction and N to P junction. But due to the light intensity, I mean the light absorption, the more electron free holes and more free electrons are created. More free electron created in P junction and more free holes created in N junction. But as we know that in reverse biased condition, the current will have no flow, or electrons will have no flow. So what will happen? They will have drift current here, and the circuit will run. So means from the drift current, the circuit will collect, the circuit will have current, and the photodiode will start to work. But there are some significant parameters of photodiodes, like quantum efficiency, detector responsivity, spectral response range, noise characteristics, response time, rise time, and gain. These are the major significant parameters to achieve high efficient photo detectors. If we talk about the rise time is the time of the detector output current to change from 10 to 90% of its final value when the optic input power variation is a step. So basically, this all these significant parameters should be in consideration to have higher efficiency. And if we talk about the significance of photodiodes, normally they are low cost and excellent linearity in output photocurrent now according to the light intensity, and they have fast response time, and also available in wide range of packages. They have low noise, mechanically rugged yet compact and lightweight, and also they are available in dual, squads, or linear arrays. And they have huge applications such as spectroscopy, photography, analytical instrumentation, optical position sensors, beam alignment, and also beam alignment basically it uses in construction sector and many areas, but it has huge use in construction sectors nowadays. Without this, the buildings and the construction manufacturer are in trouble. So, and also they have surface characterization, laser range finders, and also they have optical communications uses, and also nowadays it's are using in medical imaging instruments. So Allah subhanahu wa ta'ala said in Quran that It is He who made the sun a shining light and the moon a derived light and determined for it phases, so that you may know the number of years and account of time. Allah has not created this except in truth. He details the signs for the people who have knowledge. This one from chapter 10 and verse 5. And also at the next verse, Allah has said, indeed, in the alternation of the night and the day, and what Allah has created in the heavens and the earth are signs for people who fear Allah. Means, normally the lights Allah has created, the light, sun and moon. And if Allah doesn't create the lights, so means the photodiode are also not possible. And Allah has given us the knowledge, alhamdulillah, to create these kind of devices, to make these devices, but all the credits goes to Allah. So we praise to Allah that Allah has given us the knowledge. And from here we can define that Allah has created the lights, so only it has possible to implement the lights to create photodiode kind of devices. And I also want to repeat again that in Surah Ar-Rahman, Allah Subhanahu wa Taala said 31 times, فَبِأَيِّ عَلَاءِ رَبِّكُمَا تُكَذِّبَانِ. That means that what of the things of your creators you want to deny. So there is nothing to be denied that people has the credit to do something except Allah give us the knowledge or Allah make us possible. And here are the references. Thank you.
Okay, thank you, brother, for the presentation. Can you stop sharing? We can ask question. Who wants to ask question first? Is it clear? You can answer the question in the exam.
I want to ask, so the photo detector must be in reverse bias,
Yes.
or is it only in photodiode? Other than photodiode? No.
Only the
There is
photodiode. The photodiode basically works in reverse bias condition.
Why?
Because when it works in reverse bias condition, the gap between the energy band diagram is huge. So means the electron from N type N to P and holes from P to N is hard to recombine.
So basically there is no diffusion happen, only drift, is it?
Only drift current occurs, yes.
Can you repeat the question, the answer why? In reverse bias?
When in reverse bias condition, the Fermi level is in not same level, it changes.
The same port bias, also the Fermi level changes.
Yes. But in forward bias, the energy gap or the band gap is less compared to reverse bias condition.
So
the gap in reverse bias is higher than the forward bias. So what will happen? The electrons from conduction band to valence band will have hard to recombine with the holes. So therefore, there will have no diffusion.
why? It's easier. If it's bigger, it's even easier. The gravity, if it's the combination, you always like to go to the lowest level, so it doesn't make it will make no difference if the and the band gap is the same. You didn't change the band gap, right? When you reverse bias, do you change the band gap?
The EG remains same, but from the level P type and N type, it increases, right?
Yes. So
in this case, there will have no diffusion.
there will be no
Diffusion.
diffusion.
Yes.
Why you don't want diffusion? It's okay. Next question, because my question is like working backwards. Your mind need to work backwards. We'll go through it later. Any other question?
For this photo detector to work, do we need avalanche breakdown? We need the diode first to undergo breakdown. Uh,
Sorry, sister, I didn't understand your question.
I mean, photo detector is operated in the reverse bias condition,
Yes. Okay.
and if we increase reverse voltage, reverse bias, then there will it will break. The diode will it will damage, but we don't have to damage. Ma'am taught us about avalanche breakdown. So we have to make it undergo this avalanche breakdown. Is avalanche breakdown necessary to occur for this photodiode to work?
Uh,
Is avalanche breakdown the principle for photodiode?
I'm not sure about that, but I think we should under avalanche for. I'm not sure about that.
Okay. Types of what are the can you go to your slide? What are the types of photo detector that you put there just now?
There are three. One is photodiode, another one is spin photodiode, and another one is KPD.
APD, avalanche photodiode. APD
Yes,
is avalanche. So
avalanche.
so she's asking about the avalanche principle on photodiode. So you're supposed to be able to answer, right?
Madam, we
I
have
just
1 minute.
Yeah.
I just studied about photodiode. So
So there are other photodiodes also that do not require avalanche principle.
What time we supposed to finish the class, huh?
Ma'am, we are supposed to finish at 1.
We only have 10. So how we have? Can we go out and then come back? We'll try to finish the at least photo detector.
Yeah. Yes, ma'am, if everybody is free.
So and Allah, make sure you come back on time.
yes. Sir. I'm standby here.
Right.
Types of photodiode.
Types photodiode, yes. So you have normal photodiode, we have pin photodiode. Pin just similar to the laser, LED that we talked. Laser just the middle region you put an intrinsic semiconductor to increase. And for photodiode, photo detector, it's more crucial to have the pin, because if you make the eye region bigger, you can have more absorption. You know, sometimes I don't want to confuse us. Sometimes we use the word generation and recombination, right? And then he used the word absorption and emission. It's the same thing. Okay, generation and absorption is the same thing. Emission and recombination is the same thing. You recombine, of course, it will emit. It emit in terms of photon or phonon. So it's the same concept. Okay, so don't confuse. So you have pin photodiode, and then it will increase the efficiency. Then you have avalanche photodiode. Avalanche using the principle of avalanche that we talked before. Have we talked about the principle of avalanche before? Yes. Huh? Have we? Have I teach you what?
Yes, before see you.
Yes, we have. So we have talked about tunneling and avalanche, both. Have we?
About Zener breakdown and avalanche breakdown.
Zener
No
break.
tunneling.
And okay. But Zener breakdown, it occurs due to tunneling, right?
Yes.
Yes.
Okay, so covered, right? So good. So avalanche. So in order to increase the efficiency of photo detector, they use avalanche. Why? Number one is become faster, because when you have the slope become bigger, the drift will be faster, the electron will move faster, then you have more the more what do you call it, more collection of the free carriers. Okay, when we talk about photodetector, it's collection of free carriers, because you have generation of free carriers, right? If it's being collected, if the electron is being collected at the end site faster, then it means that the response of the photodetector is faster. right? And it's important. For example, if faster is always important. Why? For example, if you have you want to send communication, you don't want some delay or lagging. So a fast photo detector will capture all the photons coming and no delay, right? And okay, so avalanche photo detector, number one, because it will be faster, and number two, it has its own what do you call it, amplification, internal amplification, because whenever you have a photo detector, one photon will generate one free electron hole pair, right? One free electron hole pair, and one free electron, one free hole. So uh, so so one free carriers, you cannot measure the current on one free carriers, right? So for example, if like even pico ampere in terms of current, you need like millions of millions of free carriers, a lot of free carriers to get one pico amp. You can do the calculation. So it means that you need amplification. Otherwise, the circuit, you have a photo detector, but the circuit cannot measure the current because it's too small. So you need to have amplifier. Normally, if you have photo detector, you have amplifier, then you can connect to the outside world. But by using avalanche photo detector, what it means that you have internal amplification due to the what do you call it, the impact ionization. We covered in the class, impact ionization. So one electron hole pair can create many other electron hole pair. So that's creates an internal amplification. Okay, any other question to Alam on photo detector? So are you clear how the photo detector works using energy band diagram? You understand everything that Alam explained just now? Because you have no questions. Hi Iman, no question. Why?
Just one question. So the photodiode will be in reverse bias, and at some point the it will reach saturated drift current. So will the photodiode having uh, at some point will be breakdown or something like that, because it's the current flow is in the reverse, right, inside the
Actually, when it is connected in reverse bias, so it will also depend on the light intensity, the external light. So when it's equal to the energy gap, then only it will break down, and we will have a dark current.
What is equal?
When the photon intensity or the light is equivalent to the energy gap,
Intensity or the energy of the photon?
energy of the photon is equal to the energy gap.
Be careful, intensity is different thing. You got it wrong in the exam. So can you repeat again?
So when the light energy or the photon energy is equal to the energy band gap, then only it will start to have drift current.
It have to be the same or it can be bigger.
Uh, uh, Cannot be less, but can be same or bigger.
Yes. So that's why you need to say it's actually the same or bigger. Okay. Then it means that you have enough energy for the electron in the valence band to be promoted or generated to the valence band, to the conduction band, because
Yes.
where they get the energy from the photon, the incoming photon.
Photon, yes.
But I
And
think
also we
you're
have
not answering his question. Do you understand his question?
the question is about at some point the diode will break down, right? So what is the that some point? At what condition the photodiode start to break down?
You can question Anas back. It doesn't mean that the question is right. Okay. If you don't
I
understand
think
the question,
I
Breakdown means
question.
huh?
I think my question is also similar to Anas. I mean, for this photodiode to work, for the current to flow, it has to. We don't need only dark current, but we need higher current. But that will flow when the diode has undergone breakdown. So, won't the diode be damaged? I don't understand.
Alam. If you don't understand the question, ask them.
means sister is asking that when the voltage is higher, more than the breakdown voltage, then the diode will damage or no? Is it?
Yeah, we are operating in the reverse region. Do we only need the small dark current from a photodiode, or we need a larger current?
Actually,
Uh,
when we have uh, external light, or I mean light energy, then it will produce dark current. And Prof said that the dark current amount will be very less, but we need to amplify that. Then only we can use in our
yeah, it will get amplified, and finally, avalanche breakdown will occur. Uh, Avalanche breakdown.
No, no.
I
If
think.
you have normal PN junction photo detector, you have PIN avalanche. PN junction photo detector doesn't need
Uh,
avalanche to work. It can work without avalanche.
Okay, so how will it work? How can we then amplify when this current is how will a normal PN junction amplify the current in the reverse bias?
with some external circuitry, some amplifier, with the help of some
Hmm?
amplifier.
External amplifiers, not in this. Okay. Uh,
The prototype is not will amplify by itself. We need some amplifier.
only avalanche photodiode will undergo internal amplification.
Uh,
Yes.
Hmm.
You're not answering Anna's question yet.
Prof. Anas is asking that he's talking about some breakdown voltage. I'm not clear about that.
Ask
As what I understand about the a PN junction, when it has reverse biasing, when we apply a lot of voltage or electric field on the reverse bias PN junction, the material will be breakdown, right? So the it will not function as usual after that. Isn't that right? So what is the limit point of the photodiode to not break down in reverse
Okay,
bias?
to protect from damage.
Yes.
first.
Uh,
You need to say, is his statement right or wrong?
Prof, I'm not sure his question is right or wrong, but as I am, here the presenter, so I just confused about his question.
So you need to ask him until you are not confused.
So, his brother, you were asking that, to protect the diode, what is the maximum voltage? To get it damaged, right? Is it
Just
in
want to
different?
know.
Peak
Just want
inverse
to know is
voltage. Peak inverse voltage. Uh, are you talking about the peak inverse voltage? After that, if we apply any more voltage, the diode will
yes
be damaged.
breakdown damage.
Yeah,
Yes.
yeah, damaged. That is the peak inverse voltage. Uh, we need to we need to operate diode on voltages lower than peak inverse voltage. After peak inverse voltage, it will be damaged. So this is also my question, that do we have to perform this avalanche breakdown before the peak inverse voltage is reached? And how
I'm not.
can we do that?
Uh,
Alam.
Sorry, I'm not sure about that.
Okay. I actually when I'm trying to, that's why I don't understand Anna's question. So I'm hoping Alam will ask and clarify with Anas, but until the end it's not clarified. Because I think there's something you mentioned about saturated current just now, right? Mm. Why do you mention about saturated current?
Uh, because when in reverse bias, there is no diffusion, only a small minor of current due
Yes,
to the electric field.
yes. So
Uh, when, as I understand, when we apply more electric field towards the diode, the drift current at some point will the diode will at some point damage, and the drift current will flow as a normal short circuit.
But my question is, in reverse bias condition, the band gap is bigger. So it means the electron from N type to P type and holes from P type to N type is not traveling. So it means in reverse bias condition, if the voltage is also bigger, so it will not start to work unless we have the photons. Am I right, bro?
I don't understand.
So
Uh,
basically,
in
the diode
reverse
will
bias
not
condition,
damage.
uh, if we provide the voltage also, but the diode will not start to work, and the more voltage we
What?
provide, the more energy band gap will increase.
No, the energy band gap will not increase.
I, sorry,
Fermi level.
the depletion region. Sorry, the depletion region will increase.
Okay, diffusion region will increase. So
So when the depletion region will increase, so means there will have no current flow throughout the diode. So there will have no damage to the diode.
I'm trying to. You are talking something else. Anas is on something else. I'm trying to consolidate between the two. Okay. I'm trying to understand now the point of why is Anas asking that question. Do you understand? Because there's something, the question is not fully right, but I don't understand why you ask that question. It means that you don't understand something, but I don't know what you don't understand. So why you're asking that there might be too large, the current in the reverse can be too large, and in the end it will be permanently break down? Is that your question?
Yes, yes.
Okay. Yes, if you look, okay, okay. Alam, can you show the slide where the IV characteristic of a photodetector? Can you explain that? I think that will explain Anna's question. For those who have to leave the class, it's fine. For those who can stay, you can stay.
So can you please access
Oh, I need to accept?
sharing?
Okay.
Yes.
Alright. Dah. Done. Actually, photodetector is not difficult. It's very easy. It's the one of the easiest. The easiest is LED,
Okay.
followed by photodetector, then solar cell, then laser. The most difficult. Okay. Can you explain here? Can you answer Anna's question based on this graph?
When we have normally this is a diode, photodiode, and we have connected in reverse bias mode. So when it is in reverse bias mode, there will have no current flows throughout this circuitry. But we will have a small current. There is called dark current. You can see a dark current due to the electromagnetic field. So we will have just the dark current. There is
Dark current is the saturated current. Okay.
saturated current.
This
That
is
is ignorable. So that's why we have given put here 0. And when we have photons here, then means the photon energy increases. Then our the current also increases. From this curve, from current and versus the light intensity, we can see here the light intensity increases, means the photon energy increases, the current also increases. So if we have more current, that is good for us.
Can you
So if the light,
draw there? Can you show how, where's the breakdown over there? In the graph, where's the breakdown? Can you get breakdown over?
Breakdown voltage flow.
Yes, breakdown voltage. Where's the breakdown voltage and the current? Looking at the breakdown voltage.
The breakdown voltage is 0.5 volt.
There's a forward voltage. Breakdown. What is breakdown?
Uh, then -1 in reverse bias move.
Okay, no. I will answer the question. Can you unshare? I will draw. Ada question to Alam while I'm drawing? You have any? Huh?
Yes, is the photo detector construction of the diode exactly same as a normal PN this junction diode, or is something different in the construction?
Alam, do you hear the question?
Sorry, sister, can you please repeat it?
Yes. Is the construction of photo detector diode same as normal PN junction diode, or is there something different?
It has p type and n type, but it is a little bit different because it has need to have the photon absorbed, right? So the construction is normally I can draw here.
We can use any diode, and if we put light on
No,
it will
cannot,
act as okay.
cannot. It should have one part to absorb the photon energy.
Sorry.
The construction of photodiode is totally different from normal diode.
Construction.
But yeah.
What do you mean?
Because it has p type and n type, but we also need to have the photon. I mean, the place where the photon will absorb by the diode. Means
You can observe in
I better draw and I send in the group.
Okay.
But actually you can have a normal PN junction, you can have a photo detector, no problem.
We can use a normal diode, and if we put light on it, it will act as a photodiode, ma'am.
Yes. You just need to bias it, reverse bias, and make sure the lights can enter the device. So where the question is maybe where the absorption, where is the generation that will occur, the absorption, where is it will occur, which region?
In PN junction.
It's a PN junction. Most of the absorption or generation will occur in the
PN junction.
depletion region, because whenever you have PN junction, of course you have depletion region, right?
Yes.
When you reverse bias it, you have a bigger depletion region, and all the absorption will happen there. So even it's a normal PN junction, it works. But if you make it PIN, it become better. Okay. Now to answer the question of Anas, basically this is the IV, the current voltage characteristics. So this is the one that Alam was showing. So this all negative, and this is positive for voltage, this is negative voltage, right? So as you know, for what you call breakdown to occur, it need to occur at very high voltage, right? If it's an avalanche, it's happening at very high voltage. Then what happens if you breakdown will occur like this. Okay, whenever this is I, this is B, when you see this, a sudden increase in the current, this is current, right? Sudden increase in current is breakdown. So when you see here, if you look here, this current here is not breaking down yet. It's just a normal increase. So it can break down if it go further. It go further and then like this. And this is breakdown. When you say for avalanche breakdown, for avalanche photodetector, what happens is For normal PN junction, PN, this is the operating region here, inside here. Basically, you get the current here for a certain intensity, you get this much, another intensity this much, another intensity this much, right? So the intensity will determine the level of current. The higher the intensity, the more electron volt pair that we produce, right? Okay, now if it's a avalanche photodetector, what happens is you are playing like here. The operating region is here. So can you see the difference? The normal is over here before the breakdown. For avalanche photodetector, you are playing here. For example, so what do you call it? So if you have, this is like supervisor, when you have light, it will be like that. So when you operate at this voltage, here, let's say the voltage -1, -2, -3 volts. But avalanche breakdown, for you remember, for it to occur, it occurs at very high voltage, so maybe -50 volt here. So you bias at -50 volt, then you shine light into it, and then this is the current that you measure. Okay, and this current, because it's at the avalanche region here. Oh, sorry. Because it's at the avalanche region here. So a slightly what do you call it? This current can multiply very fast. So if you operate at this region, this voltage and this voltage not much difference in terms of current. But if you operate at avalanche breakdown, a slightly -51, you get a lot of current already here. But here, if it's not in the avalanche region, you change to -1 to -3, not much difference in current. But if it's in the avalanche region, only like 0.5 volt, you already get a very high difference in current. Do you understand? That's how you get extra. So for example, so this avalanche, this is avalanche photodetector. I can if I can work, I can what do you call it, bias it or use it in this region, but I won't benefit the increase in current. But if I bias it at -50 volt, I can get current of maybe 100 times more. So 100 times more compared to here. 100 times more. Okay, so which means that I don't need to have amplifier. By the same light, this one I will only get 1 milliamp, but by saying at -50, I get 100 milliamp using the same device. Okay, any question? Any question? And you should be able to draw, because I don't see the PN junction, the full PN junction. Alam, did you draw the full PN junction of a photo detector just now? Alam, did you draw just now? Alam, I'm asking you, did you draw the full PN junction?
Prof, on paper or on
the slide?
The slide.
Do you have this energy band diagram? This is what I want. Did you? I don't think you have any just now.
I have, Prof.
Huh?
I have.
You have?
Yes.
Which one?
Can I share?
Yeah, sure. Let me stop sharing. Can you share now?
Oh, this one?
Okay, this one. Yes. So can you explain how it works again?
So So basically it works in reverse bias condition, and in reverse bias condition we need to, when the light energy absorbed, then we have more free electron and we have more free hole. So
You
when we have more,
you miss. So if you have light, then what happened?
so we will have generation of free electrons and free holes, means
Okay,
free electron hole pairs.
all right.
So the more light intensity we will have, the more free hole and free electron will be generated.
Uh-huh.
So what will happen? So when the more free electron occurs and more free holes generated, then the free electrons will go to the conduction band, and free holes will go to the the, uh, the free hole and free electrons, they will start to recombine.
You combine.
So
This is the most important part. How does the photodetector work?
So when we have more free electron and more free holes, so we will have more drift current.
More drift current. So how do you get the drift current?
The free electrons will go to the valence band or the p side, and the free holes will go to the n side.
Again? How do you get the drift current?
So is it the higher the concentration of K-rays created, much more easy for the K-rays to be drifted?
No.
It will be like a normal PN junction diode. Free electron will go from P to N, minority, like in a normal reverse biased PN junction.
Again?
Free electron will flow like it will flow in a normal reverse biased PN junction diode. I mean, it will flow from P side to N side. The minority carrier will flow when it is reverse biased.
Okay. Why?
And the hole will go from this N to P.
Why? Yes, Iman.
Because it is reverse biased.
No, there must be yes, it's true, but there's a more detailed explanation. Yes, Iman.
I need to go because I need to go to the doctor's appointment
Oh,
this
okay.
afternoon.
Okay, no problem. I will record this. You can leave, Iman. Okay. Let me answer let me answer my own question. Can you stop sharing? I will share my very quickly. This your answer was not wrong, Tamana, but it's not complete. Okay.
Okay, ma'am.
Okay. So this is the PN junction of the photodetector, right? So if it's a if it's a PIN, this I region will become bigger. Okay, this I region will become bigger. If it's not, it's just PN, it's just a depletion region in the in between. Because it's reverse bias, the main, remember we talk about forward, reverse, and the main in reverse bias is drift. Why drift? Drift is due to what? How do you get drift?
Electromagnetic field.
Because of electric field, right? And what is electric field? Electric field is the difference of this energy. right? So in reverse bias, the bigger the reverse bias, the bigger is the electric field potential. So what happens is in photodetector, you have generation. So you have light coming and it will hit the semiconductor. If this light of the photon is bigger than the band gap energy, what happens is this energy will be absorbed by the electron over here, and it have enough energy to be excited to the conduction band. The same goes to the hole. Hole will have enough energy to go to the valence band. Okay. Okay. Once it's in the, so I will just draw the electron. So once the electron is once the electron is being excited to the conduction band, you can, and I remember I told you electrons are like balls, right? Who are like bubbles. So the electron see this loop and it will drift down due to the electric field. So the bigger the slope here, the steeper the slope. If the slope like this, right, the electron will flow faster. That's all. It's the same number of electron being excited, but it will go faster. So the electron here will drift to the end side and be collected. So when it's collected, you get current. So the principle of photodetector is very simple. Light coming in, which is bigger than the band energy, the electron will be the electron will be excited, will gain energy and be excited to the conduction band. Hole vice versa, it will go from the conduction to valence band, and it will drift due to the electric field. It will drift. So if it's avalanche, if it's avalanche photodetector during this time, it will impact ionize and you get extra current. Remember, I talked about avalanche breakdown before. Go and watch your video. Or I have a video inside my YouTube on avalanche, I think. So then, and when it's collected, then finish. Then you know, it's become a photodetector. Light coming in, current coming out. Okay, any question? Any question? No? Great. Okay, great. I think that's all for today. Please go and read solar cell, photodetector, laser and LEDs. I think next week I'll give you your quiz. So the quiz will be on the diode first. Okay, I haven't given any quiz on diodes. So next week quiz on diode. The week after that will be quiz on optoelectronic device. I will choose, it will be on LED and or I can choose between put both or just LED and solar cell. So your final will include laser and photodetector. Okay.
Tomorrow?
Sorry?
We have a class tomorrow?
Tomorrow?
Yeah, Wednesday. We have a
Yes,
class.
you have a class like as normal tomorrow, inshallah.
Prof,
And
this will be
on Monday we have quiz for PN Junction.
Yes, Monday I'll give you a quiz. We'll go how you call it, how do we do it? I give you after the class, I give the question. So you have half an hour to do it after the class.
Okay.
Prof, we just have to study on diode only.
For next quiz on diode only. Okay, everything on, but make sure you remember all the previous semiconductor material because it will be included indirectly.
Means intrinsic, extrinsic, all this.
So the effect of temperature and everything. Okay, but you need to be able to draw the energy band diagram. Okay,
Of PN junction.
or PN junction.
In different conditions like zero bias, forward bias, reverse bias.
Yes. Okay, so that will be on Monday. Remind me Hopefully you can remind me by Sunday or something. I forgot, and suddenly on that day I forgot to give the question. So, but after the class, after the class finish, you can have anytime half an hour. Just time yourself and then complete it. Take a photo or scan it and send it to me. And I trust that you will not open any book or open the internet. Okay.
Oh, we don't have to be on video call while we are doing the test.
No,
Oh,
I trust you. Can I trust you?
inshallah, yes, ma'am.
Yes. If
So,
not, like lightning will strike you. Okay.
so can we have some assignment?
Simon,
Yes.
for what?
We have some quiz, some assignment.
I already gave one assignment. I'm going to give the reason why I'm going to give quiz because you will not be able to handle the exam if you don't do a lot of the quizzes. You'll be shocked. Normally students are shocked. So I think one assignment is enough. You want more assignment?
No, ma'am. I don't want.
But Prof, you haven't given us any assignment yet.
No, this presentation is assignment. I'm marking you.
Oh, okay,
It's 30%.
This was our assignment, yes, ma'am.
okay.
Okay. So this is your assignment. So next is quiz. So prepare for the quiz and the final
Okay.
exam. Okay. And so next class we will go to VJT inshallah. Okay.
Okay.
Tomorrow.
Sure.
Okay. Alright.
Okay, ma'am.
So you are on time. Okay. Assalamualaikum warahmatullahi
Assalamualaikum.